So in this lecture, we are going to revisit the simple harmonic oscillator. So in a previous lecture, we solved the simple harmonic oscillator by doing a series solution of the differential equation, the time-independent Schrodinger equation. However, there is a very different and algebraic method for solving that system that was developed by Dirac. And Dirac's method uses some very clever and very useful techniques, which since then has become part and parcel of mathematics and physics. And that method is called the method of ladder operators. So let us begin with a recap of the simple harmonic oscillator. Remember that the Hamiltonian of the simple harmonic oscillator was given by p squared by 2m, the kinetic term, plus a potential term, which we can write as m omega squared x squared. So this was sometimes called k, the Hooke's constant. So the form of this Hamiltonian is a quadratic form. So both terms, this term and this term, they are quadratic. And that means that this is actually a positive definite Hamiltonian. What does that mean? For an operator to be positive definite, it means that if you take the expectation value of that operator, then that becomes a number. That number will be either 0 or greater than 0. And of course, this is very easy to prove because the left-hand side is just 1 over 2m, which is a positive constant, psi p squared psi, and the second term is half m omega squared, which is also a positive constant, then a psi x squared of psi. But of course, this we can write as p of psi, since p is a Hermitian operator, p of psi, the inner product with itself, and x of psi. Of course, being inner products, we can write this as modulus of the state p psi squared plus half m omega squared modulus x psi squared. So everything in this expression is positive, and therefore it is either 0 or positive. So that means that the eigenvalues of the Hamiltonian operator are positive. Because it's a quadratic operator, Dirac's insight was to write it in terms of some non-Hermitian operators. So what he did is that he introduced two operators. One was called A. So A is some constant chosen for convenience, and then a linear combination of x and p, which is a complex linear combination. And then its Hermitian conjugate, A dagger, is then of course given by A omega 2h bar x minus I p by m omega. Of course, it should be obvious that these two guys are Hermitian conjugate of each other. Remember that the fundamental commutation relationships are x and p, the commutator of x and p is ih bar, and of course any operator commutes with itself, and so these are the fundamental commutation relationships. Now what we can do is that using these, we can then figure out what the commutation relationship is between A and A dagger. So what is A? A is m omega by 2h bar square root, but there'll be another factor coming from A dagger, so we'll have the square root go away. So, and then we have a commutator with x plus I p divided by m omega commutator with x minus I P divided by m omega. So this becomes m omega by 2h bar. Of course, the commutator between x and x is 0. The commutator between p and p is 0. So the two commutators which will be non-zero would be the one between x and p and x. So we get two terms, and each term will have a constant. So the first term gives me this, and then we have commutator of x and p, and then the second term will be a commutator between p and x. So now what we can do is that we can pull out the constant from inside, and then we have I by m omega. So that's this thing. So we write the second term first. It's going to give me minus I h bar, and then the second term, the first term has a minus sign, so it's going to give me minus I h bar, and therefore we are going to have m omega cancelling out. I times minus I is plus 1 by 2h bar times 2h bar. So that's, we are going to have 1. So therefore, the fundamental commutation relationship imply that the commutator of A and A dagger is just 1. So let us now define another operator. Let's call it n, and n is going to be A dagger A. Now it's easy to show that n is a Hermitian operator, because if I take the dagger of n, we get A dagger A, the whole thing daggered. Of course, taking the Hermitian conjugate reverses the order of operator, so we will get A dagger times A dagger dagger, but this is A dagger A is equal to n. Therefore, n is a Hermitian operator. And it's easy to show, given everything that we have derived, that the Hamiltonian for the simple harmonic oscillator can be expressed in terms of n in this way: n plus half times h bar omega. So this is the expression for the simple. So this is the expression of the Hamiltonian for the simple harmonic oscillator. And also, because h is just n plus some constant, it's easy to see that h and n, they commute with each other, because h is nothing but n plus half times a constant, which we can factor out of the commutator. And this is going to be, this term is just a number, so this will commute with n, and of course n will commute with itself, so this is 0. So h and n commute with each other. This means that if we find psi as an eigenfunction of h, so if this is true, then this will also be an eigenfunction of n with some, with some number. It could be, let's write it as ni of psi. In other words, psi is a simultaneous eigenfunction of h and n.